Hello, everyone. Thank you for joining us today for the our 4D STEM webinar series. Today, we will focus on 4D STEM techniques for strain analysis in semiconductors. My name is Çiğdem Keskinbora. I will be your host today for this session. We have two great presentations lined up, and we are really glad to have you all here. Before we dive into the content, I would like to go over a few items to help you to navigate in our online platform and make the most out of it of this webinar. First, you'll notice a Q&A box located in the upper right corner of the screen. Throughout the webinar, feel free to type any questions that you have it. We will have the Q&A session at the end of the webinar, but you can submit your questions anytime during the presentations. As always, we will address all the questions as much as possible, but if we cannot get yours today, we will follow up with the emails. Below the Q&A box, you will find a survey sections. So your feedback is really valuable. So that's why we really want to get the feedback from you guys. So we really encourage you to take a moment and fill out the survey once the webinar is finished. And we will try to, your feedback will help us to improve the future webinars. Just below the survey, there is a resources tab where you can find an additional materials about today's topic. This is available to download at any point during and after the webinar. And last, we also, I'd like to ask to mention that the webinar will be recorded. So if you need to step away or would like to revisit the content later, the recording will be available on demand. It will be shared via email, but it will be also available in the YouTube as well. So with that, let's get started. Today's topic is again about the 4D STEM techniques for strain analysis. And we have Dr. Paolo Favia and Dr. Chupin Yu, who are our experts on advanced electron microscopy techniques for semiconductor analysis. Our first guest is Dr. Favia. She is principal researcher at IMEC, who will cover the diffraction techniques applied to strain mapping at different device processing steps. Her expertise lies on advanced electron microscopy applied to the semiconductor materials and devices. The significant part of her work focuses on the 4D STEM techniques. Paolo earned her PhD in APFL in Switzerland, and she worked as a researcher at Gatan before she joined IMEC in 2006. With this one, I would like to give the stage to Paolo so she can go over her presentation. Thanks, Paolo.
Thank you, Çiğdem, for the kind introduction and for inviting me to present at this webinar series from Thermo Fisher. And thanks to all of you for attending. In this presentation, I will talk about strain in semiconductors. The motivation to study semiconductors is that in every modern technology sector, we find semiconductors, that is in healthcare, to transportation, AI, machine learning, etc. So this is the motivation to want to study semiconductor devices. In this presentation, I will I would like to introduce you to the reason we strain a semiconductor device. I will illustrate the different techniques to measure strain with focus mainly on 10 techniques. And then I will show you examples on strain measurements on advanced semiconductor devices. So let me start. First, a quick refresher on how an MOSFET works. MOSFET is the building block of digital logic. It stands for metal oxide semiconductor field effect transistor. So the MOSFET can be seen as a tiny switch that controls the flow of electric current. It has three main parts: the source, the drain, and the gate. I will describe here the N-channel FET for simplicity. Source and drain can be seen as reservoir of electrons. When we apply a gate voltage, we create a channel between source and drain, and in this channel, electrons can flow. If we look at the current characteristics, we see that we need a certain voltage to switch on the device. So the gate voltage must cross a threshold voltage, VT, for having the device on. Also, I would like you to notice that there is this I-off current, which means that even when the device is off, some tiny leakage current is still flowing. And minimizing this leakage is very important because it wastes power when the device is idle. So what we want is a high on current, ideally, because this is will give us a very fast switching time and a very low off current, because in this way we can reduce our losses. So in conclusion, the message of this slide is that a MOSFET acts as a voltage control switch, and the key performance parameters are I-on for fast switching and I-off for less power consumption. Now, how the device performance has been optimized. Danner's law, scaling rule, showed that if we shrink all transistor dimensions and reduce voltage proportionally, transistors become faster, consume less power, and we can allow more of them on chip. So if we look at the current characteristics here, before scaling and after scaling by reducing dimensions, what we obtain is a higher I-on current, but same I-off. So faster switching, but without extra leakage. And so as transistors scale down, we can have also more transistor on a chip, and this enabled the steady performance progress described by the Moore's law that states that the number of transistors doubles roughly every 2 years. Together, this Danner's law and Moore's law created the golden age of performance scaling in transistors. More speed, because we have shorter channels, give faster switching, less power dissipation because of smaller transistor and lower power supply, give us lower energy consumption, and lower cost because of more transistors per area gives cheaper compute. So where Moore's law scaled quantity, Danner's law scaled the quality. And so this was a happy scaling era till the 130 nanometer node. At this point, something happened, which goes by the name usually of power wall. What happened? So as transistors scaled down, physical limits started to show up. And two major leakage mechanisms became significant. Gate leakage, because the gate oxide became so thin that allowed electrons to tunnel through, and source-to-drain leakage, because short channel effects allowed current to sneak across even when the device was supposed to be off. And these leakages directly increase static power consumption. So this is the characteristic I showed you in the previous slide of up in the area of Haptic scaling. And now we are at the power wall where we have loss of channel control, so the off current increases. Heavy doping was used to suppress leakages but reduce the mobility, and so less on current improvement. So to sum up the limits of scaling, we have loss of electrostatic control, which gives a high I-off, and power dissipation and leakage, which increased static power. How the industry reacted to this? So trying to overcome the power wall, new paths were created, different ones. I try to summarize here, but for sure there are others. So the main ones are strategies are beyond frequency scaling. So it's an architectural change. Instead of pushing frequency higher, designers used multi-core processor and more parallelism. In the second one, there are new device architecture with new materials, strain engineering, which is the subject of the next slides, and FinFET and gate-all-around nanosheet designs, which we will also cover a little bit. And third, specialized hardware with chips built with specific tasks. So the message is that scaling alone here is no longer sufficient after the 130 nanometer node, and innovation shifted from simple geometric shrink, following the Dennard's law, to materials, architecture, and system-level optimization. Now, there are, as I said, many strategies to overcome the power wall. One of these is strain engineering, which is what extended the CMOS scaling beyond the 90 nanometer and the 65 nanometer nodes. Here, an example of how the ion current could improve by 65% with strain with respect to a device not unstrained by keeping the same I-off. So what strain does is increases carrier mobility, boosts the transistor drive current without raising the power consumption, and enhance performance beyond the traditional scaling. There are different methods to introduce strain in a semiconductor device, for example, by embedded silicon germanium in source strain, by introducing cupping layers, or stress memorization techniques, or strain silicon layers grown on a relaxed silicon germanium. By applying strain, we tune the semiconductor mobility and therefore improve transistor performance without raising power raise. Now, let's talk about strain. Strain is defined as the relative change in length compared to the original length. It describes the variation of the crystal lattice, which can be tensile strain if we pull apart the atoms from each other, or if we push them closer together, we speak about compressive strain. I will mainly speak today about PMOS because it's where we see the strongest effect of in semiconductor devices. And the good strain is compressive, needs to be compressive in PMOS. So what does a compressive strain? The current in PMOS is driven by holes, and holes live in the valence band. So if we look at the unstrained valence band, we have that heavy holes and light holes are very close in energy and interact. With strain, we reshape the heavy hole and the light hole bands because we introduce a band splitting, which reduces the interband scattering. And also, strain increases the curvature of the upper band. And this curvature is what will lower the whole effective mass and will increase the mobility. In fact, if we, just a note on NMOS. Also with NMOS, by applying tensile strain, we can have also mobility improvement, but the mechanism is not anymore a decrease in effective mass, but is valence splitting. So on the previous slides, we saw how compressive strain modifies the PMOS valence band and lowers the whole effective mass. Now let's see what this means for actual transistor performance. If we look at the mobility, it is proportional to the mean scattering time carrier to a different energy state, and to the it's inversely proportional to the effective mass, which decrease due to the band curvature. So for PMOS, so if we decrease the effective mass and we increase the mean scattering time, the mobility will increase. And this is exactly what happens in PMOS with compressive strain, as we have seen in the previous slide. Now, if we increase mobility, of course, we increase ion. And if we increase ion, we decrease the switching time. So strain improves carrier mobility, and transistor performance improves. So strain was introduced in 2000, and here you can see a paper published in 2003 by Intel, but it's still a technology that is still used in modern advanced nodes. And for example, here you see a paper published by TSMC in 2024, where they use a 2-nanometer platform technology, and still stress engineering is used. But by the new device, the modern device are also more challenging because of the reduced dimensions and the new material. So when we study strain, we need to take that into account, and it's still a subject of research. As I said before, is also the different device architecture, and gate-all-around is one of these. So here I show you the scaling evolution of transistor from planar architecture to three-dimensional in FinFET to gate-all-around, where we obtain a better short channel control due to the gate that is wrapping around the channel. And also we can have, we can stack more channel vertically, and this gives us more active volume per footprint. So we have complex structure, and measuring strain is challenging, more and more challenging because of shapes and confined channels. At this point, I would like to pass to the second part of the presentation, where I will discuss a few strain techniques. So I will focus on time techniques, but I have just one slide showing different techniques because I think those are important because those are non-destructive technique. As you know, TM is a destructive technique. So I think it's worthy to mention them. So to measure strain, we need to measure the lattice parameter changes. When X-rays arrive on a crystal, they reflect from atomic planes and interfere. The angles where we get strong diffraction peaks follow the Bragg law. So if the lattice expands or contracts, the interplanar spacing changes, and that will be shown by a shift in the peak. So lower angle, we have tensile strain, at higher angle, compressive strain. So this technique probes average strain over large regions, and so it's ideal for thin films and blanket wafers, not really for devices. Has high sensitivity, is fast, non-destructive, and quantitative. But a drawback, a limitations is that we have low spatial resolution, so the strain that we obtain is an average. Another technique that is worthy to mention is the Raman spectroscopy. Raman doesn't measure the lattice spacing directly, but measure the vibrational frequency of the crystal, the phonons. So in an unstrained crystal, atoms vibrate at characteristic frequencies. When the lattice is stretched or compressed, these vibrational frequencies shift. And here you have an example of the pitch shift with respect to germanium, unstrained germanium. Raman is the signal of Raman can be sensitive up to a single device in a spatial mode, in nanofocusing mode. So it's a non-destructive technique, fast. Spatial resolution here is between 500 and 1000 nanometer, which is better than what we have by XRD. But it's still an average over many devices. And the technique is sensitive to temperature and tip layer stability. And now I will pass to strain analysis by TEM techniques. So to measure strain, we need to determine the lattice spacing, as I said before. And we always measure strain relative to a reference region. And depending on what we choose as reference, the meaning of this formula will change. In the first case, if the reference region is the same material as our region of interest, then, for example, a strained silicon channel or over a silicon substrate, then we can speak about mechanical strain, and this is tensile if it's positive, compressed if it's less than 0. If the reference material is different than our region of interest, for example, as here, where the reference is silicon and the region of interest is silicon germanium, then we have that when the mismatch, we talk about mismatch, and the mismatch is 0, means that the material, our silicon germanium in this case, is fully strained, because this difference will be 0. The lattice parameter of the silicon germanium matches completely the lattice parameter of silicon. If the mismatch is different than 0, then we have a certain degree of relaxation. Strain techniques There are many techniques to measure strain, and we can characterize them, for example, on how strain is extracted. So here are characterized for strain extracted by from TEM images or from diffraction patterns. I will start with the first with strain extracted from the images, and I will start with two examples where we use high resolution images. Those can be in this can happen in real space or in Fourier space. In real space, we determine the atomic column position by fitting peaks, for example, to the quotients, and then we measure the atomic displacement directly. In Fourier space, here, this is an example from Martinich from a paper in 2003. This is an example of the study of a dislocation and strain around the dislocation. So we take an image, high resolution, and then we perform a Fourier transform, and then we filter the Fourier components, and we extract the amplitude and the phase. And the phase is related to the displacement and strain. The real space approach is very precise and provides high spatial resolution, less than 1 nanometer, but it has some limitations, needs higher signal to noise ratio and aberration corrected TEM. Processing of large number of atomic columns may make the processing can be slow, but this depends on the computer and the algorithms that you use. And finally, it is limited in field of view, about 200 by 200 nanometers maximum. The Fourier-based approach, called also geometric phase analysis, is mature and robust and is widely used. Provides good spatial resolution, about 1 nanometers. In terms of limitations, we need to say that it requires high quality reference regions. It's sensitive to distortions, and also, of course, has a limited field of view since we use high resolution images. If we need in our strain analysis a larger field of view, so now, just a second. I just want to, here I listed also different processing options that can be used that are out there. There are a lot of open source, Python or MATLAB, but also licensed sources in both cases. We acquire STEM images with a STEM step near the lattice periodicity to generate moire fringes, and then we record the moire pattern, and we analyze the fringe spacing using, for example, geometric phase analysis to extract the local spacing change and then strain. Dark field holography, as I said, presents a large field of view, high spatial resolution, and is a very sensitive technique. In terms of limitation, we need to notice that the setup is quite complex, and also we need to work on two being killed. And the results are sensitive to sample quality. In the case of STEM moire, we have also a large field of view, and it's a very sensitive and fast technique, but it's limited in resolution. We are at a nanometer scale, and the technique is sensitive to scanning distortion, drift, and scanline instabilities. Also here, there are different options that you can use to process your data. So now I will pass to describe strain analysis techniques by extracting strain from diffraction pattern. Historically, one of these convergent beam electron diffraction with what strain analysis was developed. This technique needs a tilt of off zone axis of about 8-11 degrees. And so because of that, it's not really suitable for semiconductor devices. By contrast, for these time techniques, nanobeam electron diffraction, precession electron diffraction, and bezel electron diffraction are the most used to analyze strain in semiconductor devices. For this time technique is we use an electron beam to scan across our sample to obtain a STEM image, and for each scanning position we can record a diffraction pattern. So in case of nanobeam diffraction, we use a almost parallel beam, and this beam can be precessed in the case of precession electron diffraction. And in the case of bezel beam diffraction, we use a annular aperture, condenser aperture, and our diffraction pattern will be given by rings instead of spots. Important to say is that in the case of nanobeam electron diffraction without precession, we have this technique suffer of dynamical effects. Dynamical effects, we have dynamical effects when we have multiple scattering of electrons through the TEM specimen, and this can be seen in the non-uniformity in intensity in the diffraction spots. This limitation is overcome with precession and with bezel in electron diffraction. We have a medium spatial resolution in for nanobeam diffraction. It is a simple experimental setup and is still suitable for nanoscale devices and has easy interpretation. In terms of limitation, as I said before, big limitations are the dynamical effects, and it's not very precise. It can be slow technique depending on the detectors that we use. Regarding precession electron diffraction and bezel electron diffraction, those are they both have very good spatial resolution between 2 and 5 nanometers, are both suitable for nanoscale device, and minimize the dynamical effects, and those are precise techniques. The precession electron diffraction techniques, it requires a more complex alignment than bezel. And all of them have processing solutions that you can find licensed or not, open source, Python, etc. In this slide, I just compiled a table with all different techniques that I described before. I will not go into details, but I leave it here for you to look at it after. And also, I wanted to give you a few references that I listed per kind of technique, along with some general papers with a comparison. By far, it is not complete, so there are many more references out there. And this brings me to the last part of my presentation, where I would like to show you an example of measuring strain in a complex device, a gate-all-around with germanium channel. And we did this using geometric phase analysis, nano-beam electron diffraction, and vessel beam electron diffraction. And we measured the strain evolution through the gate-all-around process flow. So here, an example of how we, those are some of the steps that need to be fulfilled to fabricate a gate-all-around device. So first we start with bulk silicon wafer, then we treat, it's called ground plane formation, the surface, and then we grow our layers. Some will be our future channels, and the others are sacrificial layers that will be etched off before to release our channels. I will show that later. So we measure strain in the starting epitaxial deposition, and here I show you the mismatch in plane map along the channel, and this is the most important strain or a mismatch that we need to know, because it's where the electrons, the current flows, the direction of the channel. And then here I show you a mismatch map in the autoplane direction or growth direction. By extracting, so we extract a profile for each of these maps, and these are here from top to bottom. And the germanium channel show a mismatch in the plane direction equal to 0. And as I said before, a mismatch 0 indicates that we have a fully compressed channel. And this is also in good match with TCAD simulations. We continue the fabrication of our device, and we apply a fin cut to define PMOS and NMOS devices, and then the pattern is trenched in fin stacks. And we continue by applying a shallow trench isolation oxide, and then the oxide is etched off to reveal the fin containing the multi-layers. And we measure strain here. So the mismatch maps are indicated here for the in-plane and the out-of-plane. And if we look at the profiles, we see that in the germanium channel, the mismatch is not 0 anymore, which means that the layer has been relaxed. So by removing material at the sides of our fins, we have relaxed the channels. And this is in partial agreement with TCAD simulations. So one of the reasons we have discrepancy is also because we may have more relaxation in the TEM lamella, which is not taken into account in the simulations. So if we continue the fabrication of the device, we need to deposit the silicon germanium source on drain. And by measure, we say that the mismatch is not 0, but it's lower than what we had before, especially for the bottom germanium channel. This means that some strain has been reintroduced by depositing the source and drain. And then we release the channel by removing the sacrificial layers, and we deposit the gate all around. And finally, we measure strain again here by high resolution STEM applying geometric phase analysis. And here we see that, so we have again the mismatch in the in-plane direction and in the out-of-plane direction. And if we look at the in-plane profile, this is for the bottom channel, and this is for the top channel, and the bottom channel mismatch is almost zero, which means that we have higher strain. So we are fully straining this channel. The top one is partially strained. So if we want to sum up, we had the germanium layers were strained at the beginning. Then by etching at the material at the sides, the germanium layers were relaxed. Then strain came back by depositing the source and drain, and we still have strain when we release the channels. So this work was done some time ago, and the dimensions of these devices are still large compared to those of modern devices. In order to take this into account, in order to be able to measure strain in extremely scaled devices, we need a better spatial resolution. And I just want to show you in this slide a comparison of the nanobeam diffraction, Bessel diffraction, geometric phase analysis with the CAD simulation. The intention here was to resolve the silicon interfacial layer between two silicon germanium layers. And what we observed is that nanobeam diffraction was not able to resolve this layer, while Bessel resolved it quite well. Here where the arrows are, those correspond to the position of the silicon layer. And it's in good agreement with TCAD. In GPA, we had some signal, but it was our measurement was very noisy. And this bring me to the conclusions. I've discussed strain in silicon devices. So strain was introduced to boost carrier mobility and improve device performance. And an important point is that strain engineering is still an essential parameter for advanced and extremely scaled silicon devices. I showed you different strain techniques. So to measure strain at the nanoscale, there are many TEM techniques available, all having strong and weaker points. The choice of which one to use depends on the tool's characteristics and the questions you want to answer. If you may need a higher spatial resolution because you have an extremely scaled device, or you need better sensitivity, or you want a large field of view. So the choice of the technique may depend on this. I showed you an example of measuring strain in gate-all-around devices. So this is possible to measure strain in advanced devices, and the spatial resolution can be improved, for example, by using the Bessel beam electron diffraction. In terms of challenges, I didn't speak about them specifically, but I mentioned the relaxation in the TEM lamella which is something we need to keep in mind when we do these measurements. Spatial resolution is very important, and for some technique is limited. So it's something that is very important, especially going to extremely scaled devices. And also, we need to keep in mind that with this technique, we are limited to the 2 dimensions. And our objects under study are 3-dimensional devices. So if we want to measure strain in one plane and in the perpendicular one, we need, for example, 2 different TEM lamellas, or we need to use 3D TEM techniques. And with this, I thank you all for your attention. I would like to thank my colleagues at IMEC, Hans Mertens for providing me the Coventor animations, and Thermo Fisher Scientific for inviting me, and in particular, Shidan.
Thank you so much, Paula. Yeah, I'm really looking forward to have more discussions during the Q&A session about the presentations. And now I would like to turn it over to Dr. Yu. I'm really proud to present Chupin. So he is our application development scientist at Thermo Fisher Scientific. Before joining Thermo Fisher, as an application scientist, he completed his PhD in University of Antwerp, focusing on the 4D STEM data processing. He has a quite strong background in microscopy and 4D STEM, and today he will talk about precision like beam tilt acquisition or frame-based precision on 4D STEM and its applications. And Chupin, floor is yours.
Hello, my name is Chupin Yu. I am TEM application scientist from Thermo Fisher. And today I feel very honored to have this chance to present to you the work I've been doing from last year. It's called frame-based precision. And I would like to focus on its application in strain analysis today. So let's start with what is strain and why is this important? So strain is by definition compared to a reference region or a strain-free region, the distortion of lattice, or we can also say the distortion of how atoms are arranged. So when the atoms are compressed closer to each other, we will say this region is having the compressive strain, and vice versa, the tensile strain. Why is this important is because when the charge carrier that carries our signal, carry our electron currents, go through our semiconductor devices, the mobility, or to some sense, the speed of it, is affected by the strain present in that region. So in another word, the power dissipation and even the lifetime of these devices can be affected by different types of strain you will have in your devices. Measuring strain is somehow simple, but difficult in another way because it's very difficult to precisely tell what is the distance between atoms. So what we do is we use a derivative of that as a measurable. So that is the diffraction pattern created by electron beam. So showcase here. I'm trying to find an analogy to describe how diffraction pattern is created, and the closest and the easiest analogy I can find is actually a vinyl disc. So we know when we play the vinyl disc, the head is actually traveling through the grooves. And inside of the grooves, we have all these bumps that are creating the waveform of the sound. When the bumps are densely packed or the distance between these bumps are very close, then we will create a high-pitched sound like the bird singing. And when the distance between these bumps are pulled longer, we will hear a lower pitch sounds like cows mooing. In another word, we may not directly observe or even measure the distance between these bumps, but we can use the sound we hear eventually as an estimation of what would be the pitch size inside of that grooves. So similar to that, we're not directly measuring the lattice in a TEM, but what we do is we rely on the diffraction pattern, which is closely related, or actually inversely related to the lattice constants to measure what is the strain in your semiconductor device. In other words, when we are talking about strain measurement, what we're really doing is measuring the distance or the location of this diffraction disk or peaks, no matter how you name that. And the strain we're talking about is a distortion matrix that's connecting these two coordinate systems, one from the unstrained region and the other one from the strained region. And the terms like tensile, compressive strain, shear, rotation can be found in this distortion matrix. So that sounds easy, but there are also the difficult part that cannot be avoided by simply have a good optics or a good detector. So these are dynamic scattering patterns that comes from having a thicker sample. So you'll see these nasty contrasts inside of your diffraction disk. These are going to hinder having a good estimation of where is the center of this diffraction disk. And another difficulty is that electron is essentially quite difficult to be scattered at a higher angle. That means all these higher order diffraction disks is always going to appear weaker compared to the one at the center. So both difficulties will increase error in pinpointing the coordinates of your diffraction disk and also cause error in the final measurement of strain. The solution, on the other hand, is called precession. Precession is essentially a beam with a rotating tilt angle. So it creates diffraction patterns that are incoherently summed at all diffraction pattern that comes from this cone illumination. So its effect can be shown here, and it's quite clear that with precession, we'll be able to locate this diffraction disk or diffraction peaks at a higher angle. And also it wipes out these nasty dynamics contrast inside of your diffraction disk and leaves you with this cleaner ones. So both problems that we mentioned above, the first one is the dynamic contrast, and the second one is having only the diffraction disk closer to the center, is alleviated with precession. So it's safe to say, having precession, we can almost always get a better strain sensitivity. However, I also want to ask a second question here. That is, can we also expect a better, or even if it's not better, but equally good spatial resolution with precession? I think this is a very important question because we're dealing with semiconductor devices right now. And the size of this devices shrinks from generation to generation. So we also need to consider not just how good can we record our strain data, or how good is our sensitivity to strain, but also are we taking a trade-off from our spatial resolution of our TEM? So to test that, we run a strain measurement on this type of sample. So this is a silicon germanium multi-layer. Here we have pure silicon and two types of silicon germanium with different germanium concentration. The challenge here is, first, to map out the strain in the different layer correctly. And also, we would like to resolve this intrinsic silicon layer that is only 2 nanometer thick in between the silicon germanium layer as a challenge to their resolution. To start with, we use a convergence angle about 1.2 milliradian. So this is quite a common setup, I would say, to measure strain with. And we notice it is already capable of resolving that 2 nanometer layer. but you will also notice the edge of this layer is a bit blurry. That indicates we are right on the edge of the resolution that's good enough to resolve these layers. And the second thing we do is to introduce a tilt angle. Since we mentioned before, a precession is essentially a rotating tilt angle. So I would like to first introduce a static tilt angle to see what kind of resolution can we get with that amount of tilt angle. And as you can see here, with only 0.6 degree of tilt angle and 1.2 milliradian of convergence angle, your image is already taking a toll from the spherical aberration of your objective lens. So that's the message here, is that precession is going to lower your resolution, especially when you have a larger and larger convergence angle, when you want to push for the resolution. And the limitation here is because the spherical aberration from your objective lens system. The solution to that is use a different deflector coil than what conventional precession would use. So here, instead of using a scanning coil to do precession, we do beam tilt using a deflector above the corrector. So as you can see, the beam travels down the optical axis, and it's deflected to the side of the corrector. And when it comes through the corrector, it gains a negative amount of C3. And then it touches the objective lens. The objective lens will pull the beam back to the center of the optical axis and creating the beam tilt. And from there, it will get a positive amount of C3, or spherical aberration. And these two will cancel each other out. So maintain the good aberration-free condition for your probe. And in the last part, we use the deflector in a projection system to make sure the transmission beam is always sitting in the center of your detector. So the first thing we do after creating this, having this concept, is that we take a tilt series without compensation from the projection system to draw a Ronchigram from all the tilt angle, as you can see in this animation. And then we sum up all the Ronchigrams to get to these large figures. And we can see that from these figure that we have a aberration-free region about 40 milliradian. And as a reference, 1 degree is about 17.5 milliradian. So with this tilt scheme using the deflectors above the corrector, you can safely tilt your beam up to 1 or 2 degree, depending on your convergence angle. So another difference between the precession motion I'm promoting here and also compared to the conventional precession is the hierarchy of the motions. So since we're using the deflectors above the corrector, this is a DC deflectors. So we are limited to creating a continuous precession motion, as we know as the conventional precession. Instead, what we do here is we fix the tilt angle, and then we scan through the whole region of interest in multiple steps and changing the tilt angle in each steps to create a discrete sampling of that cone illumination. And eventually we can integrate it over the whole data set to create a similar effect of a continuous precession. So to set up that, we follow a procedure which can be executed automatically. The first step is to calibrate the beam tilt deflector strengths. So you want to make sure the X direction deflectors and the Y direction beam deflectors has the same strength, so creating a circle, not an ellipse. The second step is to calibrate the diffraction shift deflectors in a similar manner. And then you want to test whether your beam tilt unit and your diffraction shift unit can compensate each other. So without compensation, I'm doing a 8-step tilt series here. You'll see 8 or 9, including the center one, CBATs at different position. And if the compensation works, then in the end, you will get only a single circular diffraction disk because all of them are pulled back to the center, even with a different tilt. After this step, the next one is very important, is to calibrate the pivot point. So this can be done simply by changing the stage height. On the left side, you have the uncalibrated situation, and you can see, for example, this triangular structure is hopping from position to position when I change the tilt angle. And after the calibration, these features stays at where it should be, regardless what tilt angle I'm using. And another thing I want to point out is that the quality of the image is not changed even with about 1 degree tilt here. So that verify our assumption that our beam remains to be corrected even with large tilt angle. And after that, you can do your experiments with convergent beam or parallel beam depending on the situation. But here we're going to use the parallel beam or more parallel beam for strain analysis. To come back to our sample, earlier we've seen a recorded data sets or record results with a convergence angle about 1.2 milliradian. And we see earlier in the ADF image, we can resolve the 2 nanometer silicon layer that can still be found here in the strain mapping. But you will see also large artifacts, for example, layer here, that is not natural to the material. And if you pursue a better resolution with a larger convergence angle, this effect gets even worse. So you have very, very pronounced artifacts from the background, and some of the strain layer or some of the silicon germanium layer is disappearing because of this background noise. And this is because with a large convergence angle like 3.15 here, you will suffer even worse dynamic scattering effects in finding the location of your diffraction peaks or disks. So as we mentioned before, the second thing we want to try here is the frame-based precision. So let's see, without any tilt angle and with a convergence angle at 3.15 milliradians, we get a pretty good resolution without tilt. And with tilt, with 0.6 degree tilt, the resolution is still roughly the same as before, indicating the resolution is not lowered because using any beam tilt. And then we used 8-step in this frame-based precision to create this diagram. So we sum all the diffraction patterns from all the tilt angles, and we can see it creates an equally good image as before with all that tilt series. So in another word, we don't lose any resolution, but we get a much better diffraction pattern for strain analysis. And here is the result. So we have the 3 different cases with smaller convergence angle, larger convergence angle, and large convergence angle with 8-step tilt series or 8-step frame-based precision. And as we can see, the large artifacts here and there is gone in the last cases with the frame-based precision. And we also see the strain level is much more consistent across the 2 different types of silicon germanium layer compared to any other cases that comes before it. I'm also very happy to see that the strain in the X direction can be much nicer mapped out in the final case with the frame-based precision. And this is almost impossible in the 2 cases before where the background noise is so high, it's hiding the strain level in the 110 direction for both measurements. So just drawing that conclusion again, we gain resolution with larger opening angle, and we also gain strand sensitivity with frame-based precision without the need to sacrifice any of this. So besides strand, I also like to share with you two other applications that can be done with frame-based precision. The first one is orientation mapping. The orientation mapping, as you can see here, if with single acquisition, you will have this type of diffraction patterns. And with frame-based precision, the sampling of the diffraction space is expanded, and therefore the computer will have a better accuracy in understanding or figuring out what is the orientation of these crystals. And another application here is not really using precision, but a rocking beam. So I'm only tilting the beam along the direction of a certain junction here. But the effect of that is it can wipe out contrast in the horizontal direction, this diffraction contrast in the horizontal direction, and leave only the nice contrast indicating electric field that present in your sample. So in summary, we've raised a lot of questions in today's presentation. So we start with what is strand, how do we measure it, and how to increase the sensitivity. And we've talked about precision as an approach to increase sensitivity. But in the end, we took another approach, which is the frame-based precision, because we want high strand sensitivity as well as good resolution. In today's presentation, we've shown a correctable beam tilt up to 1 or 2 degrees, a programmable and fully automatic alignment setup for frame-based precision. And we've seen application in strand, which reduce noise level, the background noise as you've seen before, and hold the high spatial resolution that you get from using a larger convergence angle. And there are also other applications, such as orientation mapping and DPC electric field mapping. Both of them can benefit from having frame-based precision. And thank you very much for listening to my presentation.
Thanks, Chupin, and thanks again, Paula, for the great presentations today. So we already have some questions lined up, but before I start to ask the questions, I would like to remind you all, if you have further questions, so there is a Q&A box on the in the upper right corner of your screen, so you can just type the questions anytime. We'll try to answer them as much as we can in this session, but otherwise we will get back to you with the answers in email. So with that, I think I can ask some of the questions. I was wondering, what can you learn from the dynamical effects observed in the 4D STEM nanobeam diffraction, and how they are problematic or helpful for the strain analysis? I think this is for you both.
In my case, those are more problematic. That's the reason why we are moving away a little bit from the nanobeam diffraction without precision, because the spots in the diffraction pattern have an intensity that is not uniform due to those dynamical effects. So I guess the algorithm that then calculates the position of these spots doesn't work perfectly, and this induces noise in the results. But maybe Chupin has something else to add. Would you agree?
No, yeah, I agree with you. That's more problematic than helpful.
But I think it's a very good question because these dynamic effects certainly carry some lattice information, so including the periodicity, strain. The problem is that the processing software algorithm that we're using is not taking into account of how the lattice or your crystal periodicity contribute to a dynamic effect. So we cannot really use this information. So most of the effort we're doing, including precision or from the processing side as well, is to try to remove this contrast.
Thank you. We had very similar questions in the morning session as well. And the question is, I would like to ask, what is the optimum range of sample thickness for the strain analysis?
So regarding when we prepare a TEM lamella, we may have relaxation of strain. So this is a concern. And so ideally, we would like to have a thickness greater than 100 nanometer. In practice, this is not possible when we measure strain in a device. So the lamella, the thickness of the lamella that we usually use is between 40 and 60 nanometers. And this is still okay for channels that are, for example, in between source and drain, because source and drain will compress and will keep the channel strained, even though in the other direction we may have some relaxation. But as I said in the presentation, the strain that we are mostly interested in is the one along the channel because this is the direction where the current flows.
Thank you. Were strain measurement results from TM matched with the electrical characteristics of the device?
In this particular case, not. But this is something that we want to do, and sometimes we do, because we are able to prepare a TEM lamella on a specimen, on a device that has been electrically characterized. So we can really, when we do sample preparation, we can really aim for a specific device. So this is something that, it's a very good question. It's something that we will do in future.
Chupin, I think this question is for you. So does frame-based precession also work without a corrector as well?
Yes, it does. But of course, like I said in the presentation, if you do without the corrector, you will suffer from abrasion or spherical abrasion from your objective lens. This cannot be avoided if you don't have a probe corrector, but the concept of frame-based precision can still be performed without a corrector. Yeah.
Mm-hmm. So basically, you can also use it in with the Talos systems as well, and besides the corrected systems. Yeah. Okay. Another question. Could you clarify whether precision or accuracy is more critical for your specific use cases, Paula?
So precision is related to the reproducibility of the measure. Of course, I would like to have both, but I have the privilege to be able to measure samples while at different steps in the fabrication of the device. So what we often do, we compare one device with the other. And so I think that on this regard, precision is more important. Of course, if we can a better accuracy will for sure allow us to relate strain to the mobility measurement. So that will be also an asset.
So I think we can answer a couple of more questions, and which we have very similar in the morning as well. Is it possible to differentiate lattice contrast change due to the silicon germanium intermixing or strain effects that you see it?
I think it's possible. For example, if we have silicon and on top of silicon we have germanium, or what we measure the mismatch. So remember that the measurement that we do is we always need a reference. So if the germanium is fully strained, we will measure a mismatch that is 0. But if we have some relaxation, then we measure a mismatch that is greater than 0. Now, what happens if you have silicon germanium? In that case, we will measure something that is in between. We will need to make sure. We will need to check, do a second measurement, a chemical measurement to measure the content of germanium in that case. But it is possible to distinguish, I believe.
Is it also your experience, Chupin?
I'm a little bit unfamiliar with the term intermixing, but my interpretation is that if you have silicon germanium and you know the concentration, seen in the literature that people say you can calculate what is the lattice constant is based on the concentration alone. So maybe you can have an estimation of what is the predicted strain should be and versus what is that you measure. So the difference would be due to the environment. I'm not sure if that's answering the question.
In general, multimodality is quite important aspect in here, right? So it's not just strain measurements itself. You have to combine it with the different signals, and then complementarily you can have a better answer.
Yeah.
So another question: what would you take into account if you want to measure the strain in the nanoparticles? Would the setup will be different?
My concern, yeah, sorry, go ahead.
Oh, okay. Yeah, so I think theoretically it's the same, but I also have a concern that when you're dealing with nanoparticle, then the thickness of the particle obviously would change quite a lot when you measuring from the center of the particle or the edge. And something to bear in mind is that your strain measurement is always going to be affected by background signals. And because of the thickness variation, your background will also be different. And maybe you're measuring a strain relaxation from the center to the edge, but there is a high chance it's actually coming from the background level is different instead of having really a lattice constant variation. So that's something to keep in mind.
I guess the setup would be the same, but yeah, I would be concerned on where to find which reference to use. It's anyway, it's a relative measurement. So yeah, maybe we can take the central part with respect to the rest.
Maybe one last question before we close the session. So do you perform post-alignment to the diffraction pattern? I think this is for the frame-based precession. Chupin.
Yeah, so what I would do is I would try to make sure we do beam tilt, which translates in the diffraction space a shift to your direct beam, right? And then we compensate that shift with the deflector in the projection system. So what I would do instead of doing post-alignment for the diffraction pattern is to do this compensation as precise as possible. And the reason is because when we're dealing with strain analysis, strain measurement, a lot of time we're measuring the peak position or this diffraction disk position to sub-pixel level. And I think when you're doing post-alignment, you're throwing in another source of error, which is almost as the same magnitude as the precision you want to go after. And so I wouldn't trust the strain result as much if I'm doing post-alignment. Mm-hmm.
Thank you. And we can close slowly. So I would like to thank our speakers, and also I would like to thank our attendees for joining today, and also for the great questions. Before we wrap up, I would like to say a couple of more things as a reminder. So we encourage you to download the materials available in the resources section, but also you can see the link about the previous 4D STEM webinars. So feel free to go and watch them as well. There's also a lot of good information you can hear from there. And also, we really appreciate your feedback. And we would like to improve our feature contents webinar. So that's why please take a moment and fill out a brief survey at the end of the session. So with that, I think once again, thank you for your participation, and I wish you a great day. Thanks.